A binary adder. A binary adder is a digital circuit that produces the arithmetic sum of two binary numbers. It can be constructed with full adders connected in cascade, with the output carry from each full adder connected to the input carry of the next full adder in the chain. The figure shows the interconnection of the four full adder FA circuits to produce a 4-bit binary ripple carry adder. The equivalent bits of A and the addend bits of B are designated by subscripts number from right to left, with subscript 0 denoted the least significant bit. The carry are connected in a chain through the full adder. The input carry to the adder is C0 and it ripples through the full adder to the output carry C4. The S output generates a required sum bit, and n bit adder requires n full adder with each output carry connected to the input carry of the next higher order full adder. To demonstrate with a specific example, consider the two binary numbers A is equal to 1101 and B is equal to 1100. Their sum S011 is formed with the 4-bit adder as follows. As you see in the table, subscript I is equal to 0, 1, 2, 3 denotes the position of the bits at 0 position, first position, second position and third position. Input carry denoted by Ci and agent is Ai and addend is Bi. A is equal to 1101, B is equal to 1100. We want to add A and B, and the sum goes into S and carry goes to in C. I plus 1 means output carry. When we add the first two bits 1 1, it generates 0 and 1 carry. 0 goes into the sum bit and 1 goes into the carry bits. In next position we add 3 1 bits and it generates 1 1 as the output. Sum bit becomes 1 and carry bit becomes 1. This carry goes to the next bits of A and B, and when we add next bits of A and B which are both 0 0 with the carry 1, it produces 1 in the sum bit and zeros in the carry bit, as there is no carry generated. In the last bits of A and B, when we added last bits of A and B which are 1 0 with carry 0, it produces 1 in the sum bit and 0 in the carry bits. The bits are added with full adders starting from the least significant position subscript 0 to form the sum bit and carry bit. The input carry C0 in the least significant position must be 0. The value of Ci plus 1 in a given significant position is the output carry of the full adder. This value is transferred into input carry of the full adder that adds the bits or higher significant position to the left. The sum bits are thus generated starting from the rightmost position and are available as soon as the corresponding previous carry bit is generated. All the carries must be generated from the correct sum bits to appear at the outputs. The 4-bit adder is a typical example of a standard component. It can be used in many applications involving arithmetic operations. Observe that design of this circuit by the classical method would require a truth table with 2 power 9 is equal to 512 entries since there are 9 inputs to the circuit. By using an iterative method of cascading a standard function, it is possible to obtain a simple and straightforward implementation. Carry propagation. The addition of two binary numbers in parallel implies that all the bits of the AND and addends are available from computation at the same time. As in many combination circuits, the signal must propagate through the gates before the correct output sum is available in the output terminal. The total propagation time is equal to the propagation delay of the typical gate. Of a typical gate times the number of gates level in the circuits. The longest propagation delay time in an adder is the time it takes the carry to propagate through the full adders. Since each bit of the sum output depends on the value of the input carry, the value of Si at any given stage in the adder will be in its steady state final value only after the input carry to, to that stage has been propagated. In this regard, consider output S3. Inputs A3 and B3 are available as soon as input signal are applied to the adder. However, input carry C3 does not settle to its final value until C2 is available from the previous stage. Similarly, C2 has to wait for Ci and so on down to C0. Thus, only after the carry propagation and ripples through all stages will the last output S3 and carry C4 settle to their final correct value. It means अगर आप बिट्स को ऐड करना चाह रहे हैं तो आप आखिरी बिट्स को ऐड करने के लिए आपको पहले वाली बिट से जनरेट होने वाली कैरीज की जो है वो ज़रूरत पड़ती है। आप पहली 2 बिट्स को ऐड करेंगे, अगर वहाँ से कोई कैरी जनरेट होती है तो वो नेक्स्ट 2 बिट्स में के साथ ऐड होगी। इसका मतलब ये है कि नेक्स्ट 2 बिट्स को आप उस वक्त तक ऐड नहीं कर सकते जब तक उससे प्रीवियस वाली जो 2 बिट्स हैं वो ऐड होने के बाद कोई कैरी जनरेट ना करें। The number of gate levels for the carry propagation can be found from the circuit of the full adder. The circuit is redrawn with different labels as shown in this figure. For convenience, the input and output variables use the subscript I to denote a typical stage of the adder. The signals at Pi and the signals at Pi and Gi settle to their steady state values after they propagate through their respective gates. These two signals are common to all and depends only on the input agent and addend bits. The signal from the input carry Ci to the output carry Ci plus 1 propagates through an AND gate and an OR gate, which constitute two gate levels. If there are 4 full adder in the adder, the output carry C4 would have 2 multiplied by 4 is equal to 8 gate levels from C0 to C4. For an n-bit adder, there are 2 n gate levels for the carry to propagate from input to output. The carry propagation time is an important attribute of the adder because it limits the speed with which two numbers are added, although the adder, or for that matter any combinational circuit, will always have some value at its output terminals. The outputs will not be correct unless the signal are given enough time to propagate through the gates connected from the input to the outputs. Since all other arithmetic operations are implemented by successive additions, the time consumed during the addition process is critical. An obvious for reducing the carry propagation delay time is to employ faster gates with reduced delays. However, physical circuits have a limit to their capability. Another solution is to increase the complexity of equipment in such a way that the carry delay time is reduced. There are several techniques for reducing the carry propagation time in a parallel adder. The most widely used techniques employs the principle of carry look ahead logic. Consider the circuit of the full adder as was shown see in the previous diagram. If we define two new binary variables, pi is equal to a exclusive b and for sum, and gi is equal to a multiplied by b for carry. The output sum and carry can be respectively be expressed as Si is equal to Pi exclusive or Ci, and the carry Ci plus 1 is equal to Gi plus Pi Ci, where Gi is called a carry generate and it produces a carry of 1 when both Ai and Bi are 1. Regardless of the input carry Ci, Pi is called a carry propagates because it determines whether a carry into stage I will propagates into stage I plus 1 means next stage, whether an assertion of Ci will propagate to an assertion of Ci plus 1. We now write the Boolean function for the carry output of each state and substitute the value of each Ci from the previous equation. C0 is equal to input carry. This is our initial carry. Ci next carry is C1. It depends on is equal to Ci is equal to G0 plus P0 C0. It means C1 depends upon the first bits of two numbers. C2 is equal to Gi plus P1 C1, and if we put the values of C1 we get G1 plus Pi into G0 plus P0 C0 is equal to Gi plus P1 G0 plus P1 P0 C0. Similarly, C3 means third carry depends on the previous stage, which is the second stage, and its equation is C3 is equal to G2 plus P2 C2. Now we put the value of C2, we get G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. Similarly, C4, the last carry of fifth bit number depends on its previous bits. So the equation of C4 is equal to G3 plus P3 C3. Now we put the value of C3 and the equation becomes G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 plus P3 P2 P1 P0 C0, and so on for the carriers C5 C6 C7 up to the number of bits. Since the Boolean function for each output carry is expressed in sum of products form, each function can be implemented with one level of AND gate followed by an OR gate, or by a two-level NAND gates. The four Boolean functions for C1, C2, C3 and C4 are implemented in carry look ahead generator shown in the picture on the next slide. Note that this circuit can add in less time because C3 does not have to wait for C2 and C1 to propagate. In fact, C3 is propagated at the same time as C1 and C2. This gain in speed of operation is achieved at the expense of additional complexity, a complex hardware. The construction of a 4-bit adder with the carry look-ahead scheme is shown in this figure. Each sum output requires two exclusive OR gates. The output of the first exclusive OR gate generates the PI variable and the AND gate generates the GI variable. The carries are propagated through the carry look-ahead generator and applies as inputs to the second exclusive OR gate. All output carries are generated after a delay through two levels of gates. Thus, output Si through S3 have equal propagation delay times. The two-level circuits of the output carry C4 is now shown. This circuit can easily be derived by the equation substitution method. This is a picture of a 4-bit adder with carry look ahead adder where B3, A3, B2, A2, B1, A1, B0, A0, these are the bits of two numbers A and B. A0, B0 means the first two bits of A and B. A1, B1 means the second two bits of A and B. B2 and B3 means the third bits of A and B. Similarly, B3 and A3 means the fourth bits of A and B. C0 denotes the initial carry which is a input carry. So C0 initial carry produces C0 because it does not depend on any bits, and B0 A0 is equal to P0 G0 and PI AI is equal to P1 G1, which is shown in carry look ahead error, and it produces the carry C1. Similarly, next stage carry produces carry C2, and next stage carry C3, and the last stage produces the carry C4. Half subtractor. Subtracting a single bit binary value y from another binary value x produces a difference bit d and a borrow out bit b out. The operation is called half subtraction, and the circuit to realize it is called a half subtractor. The simplified sum of products expansions are D is equal to x into xy is equal to sum of m into 1 0 d is equal to, which becomes d is equal to x bar y plus x y complement, and the bar bit, and it becomes d is equal to x exclusive y, and the bar bit b becomes x complement y. We construct the truth table of a half subtractor. We see that if we have two inputs x and y, which are 0 0 0 1 1 0 1 1, the outputs d and b becomes, when we add first two bits 0 0, it produces, when we subtract first two bits, it produces a difference 0 and a 0 carry. Similarly, when we subtract 1 from the 0, the difference bit becomes 1, and we need a carry to subtract 1 from the 0, so b out becomes 1. Similarly, when we subtract 1 0, it produces the output 1 0 1 goes into the difference bit and 0 goes into the bar bit. When we subtract 1 from 1, it produces 0 difference and 0 borrow bit b. This is the block diagram of a half subtractor. In a half subtractor, we inputs two numbers x and y, and it produces two outputs d and b out. The logic diagram implementation of these two expressions using basic gate is shown in this figure. It can also be implemented using an exclusive OR gate and a AND gate as indicated in this figure. Full subtractor. A full subtractor has three inputs and two outputs. X, Y, and Z are the inputs to be subtracted, in which Z represent borrow from the next stage. D and B are the outputs. The block diagram of a full subtractor is shown on the next page. Table represents the truth table for a full subtractor with three inputs x, y, and z, where z is equal to b in, and two outputs d difference and b out, where d is equal to x complement y complement z plus x complement y z complement plus x y complement z complement plus x y z, and b borrow out is equal to x complement z plus x complement y plus y z. A full subtractor circuit using AND OR gates x, y, and z and b in R z is shown in this figure. We implemented these full subtractor circuits by using AND gates and OR gates. And the block diagram of full subtractor shows that we have two inputs and a third input as a b in, which is equal to z, and it produces two outputs d and b out. We also implement the full subtractor circuit using exclusive OR gates, and the figure shows Here how to implement we full subtracted by using exclusive OR gates. Binary subtractor. The subtraction of unsigned binary number can be done most conveniently by means of complement as discussion uh, in chapter 1. Remember that the subtraction a minus b can be done by taking the 2's complement of b and adding it to a. The 2's complement can be obtained by taking the 1's complement and adding 1 to the least significant pair of bits. The 1's complement can be implemented with inverters and 1 can be added to the sum through the input carry. The circuit for subtraction a minus b consists of an adder with inverters placed between each data input b and the corresponding input of the full adder. The input carry C0 must be equal to 1 when subtraction is performed. The operation thus performs becomes A plus the 1's complement of B plus 1. This is equal to A plus the 2's complement of B. For unsigned numbers, the given a minus b if a is equal to greater than or equal to b, or the 2's complement of b minus a if a less than b. For signed numbers, the result is a minus b provides that there is no overflow. The addition and subtraction operations can be combined into one circuit with one common binary adder by including an exclusive OR gate with each full adder. Subtraction can be realized using an adder by controlling inputs to a parallel adder. This is done by including an exclusive OR gate with each full adder. The mode input M controls the operation. When M is equal to 0, we have B exclusive 0 is equal to B. The full adder receives the value of B. The input carry is 0 and the circuit performs A plus B. When M is equal to 1, we have B exclusive 1 is equal to B complement. The full adder receives the value of B complement. The input carry C0 is 1 and the circuit performs A plus the 2's complement of B. A plus 1's complement of B plus 1. The exclusive OR with output V is for detecting an overflow. This figure shows a 4-bit adder subtractor circuit. By changing yi to bi and making ci is equal to 1, 2's complement of bi input is obtained. Now addition of 2's complement of bi to ai results in addition operation. In order to achieve this, a control input M is used. Consider the table expression of xi and yi can be obtained using K-map. The resulting expressions are xi is equal to ai, yi is equal to bi exclusive m, and ci is equal to m. These equations are implemented to obtain an adder subtractor circuit and is shown in this figure. It is worth noting that binary numbers in the signed complement system are added and subtracted by the same basic addition and subtraction rules as are unsigned numbers. Therefore, computer needs only one common hardware circuit to handle both types of arithmetic. The user or programmer must interpret the result of such addition or subtraction differently depending on whether it is assumed that the numbers are signed or unsigned. Overflow. When two numbers with n bits each are added and the sum is a number occupying n plus 1 digits, we say that an overflow occurs. Means if 4-bit numbers are at two 4-bit numbers are added and the result is a 5-bit number, then we say that an overflow is occurred. This is true for binary or decimal numbers, signed or unsigned. When the addition is performed with paper and pencil, and overflow is not a problem, since there is no limit by the width of the page to write down the sum. Overflow is a problem in digital computers because the number of bits that holds the number is finite and a result that contains n plus 1 bits cannot be accommodated by an n-bit word. For this reason, many computers detect the occurrence of an overflow, and when it occurs, a corresponding flip-flop is set that can then be checked by the user. The detection of an overflow after the addition of two binary numbers depend on whether the numbers are considered to be signed or unsigned. When two unsigned numbers are added, an overflow is detected from the end carry out of the most significant position. In this case of signed number, two details are important. The leftmost bit always represents the sign and negative numbers are in 2's complement form. Means is the most significant bit or the leftmost bit is 1, the number is negative. If 0, the number is positive. When two sign numbers are added, the sign bit is treated as a part of the number and the end carry does not indicate an overflow. An overflow cannot occur after an addition. If one number is positive and the other is negative, since adding a positive number to a negative number produces a result whose magnitude is smaller than the larger of the two original numbers. An overflow may occur if the two numbers added are both positive or both negative. To see how this can happen, consider the following example. Two signed binary numbers plus 70 and plus 80 are stored in two 8-bit registers. The range of numbers that each register can accommodate is from binary plus 127 to binary minus 128. Since the number of the two number is plus 150, it exceeded the capacity of an 8-bit register. This is also true for minus 70 and minus 80. The two additions in binary are shown next together with the last two carries. Note that the 8-bit result that should have been positive has a negative sign bit, the 8th bit, and the 8th bit result that should have been negative has a positive sign. If, however, the carryout of the sign bit position is taken as the sign bit of the result, then the ninth bit answer so obtained will be correct. But since the answer cannot be accommodated within 8 bits, we say that an overflow has occurred. It means when we add minus 70 and minus 80, and it produces a result minus 150, and in binary it produces the result 01001110, and the most significant bit or the leftmost bit of minus 150 is equal to 0. 0 means that number is a positive, but this number is a negative number, so here overflow is occurred. Similarly, when we add two positive numbers 70 and 80, the result is plus 150, and the binary of 150 becomes 01101001, and the most significant bit or the leftmost bit is equal to 1, which indicates in signs number is as a negative number. So it gives us that 150 is a negative number, and uh, which is a wrong answer. So an overflow is occurred in this situation. An overflow condition can be detected by observing the carry into the sign bit position and the carry out of the sign bit position. If these two carries are not equal, an overflow has occurred. This is indicated in the example in which the two carries are explicitly shown. If the two carries are applied to an exclusive OR gate, an overflow is detected when the output of the gate is equal to 1. For this method, we work correctly. The 2's complement of negative number must be computed by taking the 1's complement and adding 1. This takes care of the condition when the maximum negative number is complemented. The binary adder subtractor circuit with output C and V. If the two binary numbers are considered to be unsigned, then the C bit detects a carry after addition or a borrow after subtraction. If the numbers are considered to be signed, then the V bit detects an overflow if V is equal to 0. After an addition or subtraction, then no overflow occurs and the N bit result is correct. If v is equal to 1, then the result of the operation contains n plus 1 bits, but only the rightmost n bits of the number fit in the space available. So an overflow has occurred. The n plus 1 bit in the actual sign and has been shifted out of the position. Next topic is decimal adder. Computers are calculators that perform arithmetic operations directly in the decimal number system, represent decimal number in binary coded form. An adder for such a computer must employ arithmetic circuit that accept coded decimal numbers and represent result in the same code. For binary addition, it is sufficient to consider a pair of significant bits together with the previous carry. A decimal adder requires a minimum of 9 inputs and 5 outputs. 9 inputs, 8 inputs for the BCDs and 1 carry in, since 4 bits are required to code it with decimal bits. 5 outputs, where 4 outputs for 1 BCD and 1 carry out. Since 4 bits require to code each decimal digit and the circuit must have an input and output carry, there is a wide variety of possible decimal adder circuits. It depends upon the code used to represent the decimal digits. BCD adder. Here is we examine a decimal adder for the BCD code. Consider the arithmetic addition of two decimal digits in BCD together with an input carry from a previous stage. Since each input digit does not exceed 9, the output sum cannot be generated at 9 plus 9 plus 1 is equal to 19. The 1 in the sum being an input carry. Suppose we apply two BCD digits to a 4-bit binary adder. The adder will form the sum in binary and produces a result that ranges from 0 through 19. These binary numbers are listed uh, in the table and are labeled by symbols K, Z2, Z4, Z8 and Z1. K is the carry and the subscript under the letter Z represents the weights 1, 2, 4 and 8. That can be assigned to the 4 bits in the BCD code. The column under output sum of two decimal digits must be represented in BCD and should appear in the form listed in the column under BCD sum. This is a table where Z1, Z2, Z3, Z3, Z4, Z and Z1, Z2, Z4, Z8, where 1, 2, 4, 8 are the weights and K is the carryout. Basically, sum represented by S1, S2, S4, S8, where 1, 2, 4 and 8 are the weights of the sum digits and C and represent the carryout. The problem is to find a rule by which the binary sum is converted to the correct BCD digit represent of the number in the BCD sum. In examining the contents of the table, it becomes apparent that when the binary sum is equal to or less than 1001, the corresponding BCD number is identical and therefore no conversion is needed. When the binary sum is greater than 1001, we obtain an invalid BCD representation. The addition of binary 60110 to the binary sum converts it to the correct BCD representation and also produces an output carry as required. We also discussed this thing in chapter 1. The logic circuit that detects the necessary correction can be derived from the entries in the table. It is obvious that a correction is needed when the binary sum has an output carry k is equal to 1. The other 6 combinations from 0101 through 1111 that need to correct have a 1 in position Z8 to distinguish them from binary 001 and 1001, which also have a 1 in position Z8. We specifically further that either Z4 or Z2 must have a 1. The condition for a correction and an output carry can be expressed by the Boolean function. C is equal to K plus Z4 Z8 plus Z2 Z8. When C is equal to 1, it is necessary to add 0110 to the binary sum and produces an output carry for the next stage. A BCD adder that adds two BCD digits and produces a sum digit in BCD is shown in a picture on the next page. The two decimal digits together with the input carry are first added in the top 4-bit adder to produces the binary sum. When the output carry is equal to 0, nothing is added to the binary sum. When it is equal to 1, binary 0110 is added to the binary sum through the bottom 4-bit adder. The output carry generated from the bottom adder can be ignored since it supplies information already available at the output carry terminal. A decimal parallel adder that adds n decimal digits needs n BCD adder stages. The output carry from one stage must be connected to the input carry of the next higher stage. This is the block diagram of a BCD adder, and we see that here we have two stage uh, upper 4-bit binary adder and a lower 4-bit binary adder.